Welcome to The Explainer. Today, we're going to dive into a really fundamental question in data science. How do you make the absolute best guess when you don't have all the information? We'll be breaking down a statistical powerhouse that helps us do just that, the Maximum A Posteriori Estimator, or MAP for short. We're just flooded with data these days, right? From training massive AI models to doing super precise science, we're always facing the same core challenge. How do we cut through all the noise and find the single best explanation for what the data is telling us? What's the best guess? Well, this whole process has a name, parameter estimation. And here's a super simple way to think about it. Imagine you want to know the true temperature of a room. Your thermometer, that's your estimator. It's the tool you're using. The number it shows you is the estimate. And the goal, obviously, is to get that estimate as close as possible to the real temperature. This is the absolute heart of machine learning, where the model's parameters are like all these little internal knobs, and estimation is just the process of tuning those knobs to perfectly fit the data. Okay, so to really get our heads around MLP, we first have to talk about the classic, the default approach that so many other methods are built on top of, and that's the maximum likelihood method, or ML. The idea behind maximum likelihood is honestly really simple and pretty powerful. You just look at the data you've gathered, and you ask a very straightforward question. What version of my model, what settings for my parameters, would make the data I'm seeing right now seem as probable as possible? And then, boom, you just pick those parameters. It's all about making your data look as likely as it can. But here's the catch. This common sense approach has a really big weakness. Because it treats every single piece of data with equal importance, it can get totally thrown off course by weird, unusual data points, outliers. And that can lead to models that just don't capture the real pattern at all. And this right here is the perfect illustration of that problem. Look at this. We've got a whole cluster of data points that are clearly showing some kind of trend. But because maximum likelihood is trying its best to account for every single point, that one lone outlier way off in the corner just yanks the entire best fit line towards it. The result is a line that completely misrepresents what's actually going on. So to solve this, we actually need a totally different way of thinking. It's a bit of a philosophical shift in how we even approach probability, and that brings us to the Bayesian way of looking at the world. The classical view, what we call the frequentist view, asks something like, given the true temperature of the room is 21 degrees, what's the chance my thermometer will read 21 degrees? And that's basically what ML does. But Bayesians, they flip the entire question on its head. They say, look, the data is fixed. My thermometer did read 21 degrees. The real uncertainty is the true temperature. So they ask, given my thermometer says 21, what's the probability the room is actually 21? Or maybe 20 or 22? It's a really subtle shift, but it changes everything. And what powers this whole shift is Bayes' theorem. You can think of it like a recipe for updating your beliefs. As you can see in the formula, our final belief, which we call the posterior, is just a mix of our starting belief, the prior, and the new evidence we get from our data, the likelihood. It's a formal, mathematical way to blend what you already think with what you just saw. And this brings us right to our solution, an estimator that perfectly captures this Bayesian philosophy, the Maximum A Posteriori, or MAP estimator. Now, the cool thing is, MAP doesn't just throw out the maximum likelihood idea. Nope. It actually starts with it. It uses that same likelihood, that probability of the data, given our parameters, to represent the evidence that's coming straight from our dataset. But here's the game changer. We add a prior. This is our chance to bring in our own existing knowledge, or even just a reasonable belief, about what the parameters should look like before we even see a single data point. It could be anything from, hey, this parameter should probably be close to 0, to this value has to be positive. So the goal of MAP is to find the parameter values that maximize the combination of both the likelihood and the prior. We're not just trying to fit the data at all costs anymore. We're looking for a balance, a kind of compromise between the evidence from the data and our own starting beliefs. And this is such a crucial point. The prior acts as a regularizer. In machine learning, that's a super powerful tool to stop a model from overfitting. It's like an anchor, right? It keeps the model from getting pulled too far in some weird direction by outliers or noise, and it keeps the final estimate grounded in what we believe is reasonable. So how does MAP stack up against other methods? Where does it really fit into the bigger picture of statistics? This is where it all comes together so elegantly. Let's do a little thought experiment. What if we don't really have any strong prior knowledge? What if our starting belief is just, I have no idea? Any parameter value is just as likely as any other. We call this a uniform or non-informative prior. Well, if that prior is totally flat and it gives every parameter the exact same probability, then trying to maximize the combination of likelihood and prior is the exact same thing as just maximizing the likelihood by itself. So in that situation, MAP just collapses and becomes identical to maximum likelihood. It's an amazing way to see that ML is really just a special case of MAP where you start by assuming you know absolutely nothing. And this table just lays out the whole landscape of estimation perfectly. ML gives you a single answer. It finds the highest peak on the mountain. MAP also gives you a single answer, but your prior is like a base camp. It biases where you start your search. But a full Bayesian analysis? That doesn't just give you the peak, it gives you a complete topographical map of the entire mountain range, showing you all the possibilities. So while MAP is incredibly powerful, it's important to remember it's still giving you a point estimate, just one single most probable answer. A full Bayesian analysis goes a step further. It gives you a whole distribution of plausible answers. And that lets you measure your uncertainty with things like a credible interval, which is a range where you can say you're maybe 95% confident the true value actually is. So at the end of the day, what's more valuable when you're trying to understand something? A single definitive sounding answer or a complete map of all the possibilities? MAP gives us this incredible practical bridge right between the simplicity of maximum likelihood and the richness of a full Bayesian approach. It gives us a single answer, sure, but it's an answer that's more robust, more grounded, and smarter because of our prior knowledge.